Right, good morning, class. Angelo, to be specific. My name is Rico, okay? Federico de la Peña. You just call me Rico, alright? So I'm also recording this lecture, right, for later viewing. Right, basically, this is more of a tutorial than a lecture. We will be just discussing the exercise for Module 1. Right. This first exercise is about the hazard maps and ground motions. Okay. And these are the things that you will usually encounter once you start working with particularly engineering projects, which require seismic analysis. Right, so I don't have a PowerPoint, I just have a Word document. This is also uploaded in Blackboard. Okay. Right, basically our objective in this exercise is we should be able to explain the limitations of hazard maps. Okay. For me, in my experience, so I'm also working in DPWH, and I routinely check geohazard, geologic, geotechnical reports, and this part is always abused. Engineers, geologists usually just solely rely on the hazard map. Okay? They don't bother actually doing a detailed or site visit. Okay? And that's a very dangerous practice. Some hazards can be only seen once you actually go to the field. Okay? Seismicity data, alright, so we'll also be talking about how to obtain some seismicity data, particularly earthquake records. Also calculate some basic ground motion parameters. Okay. Actually, ground motion parameters, in layman's term, this is the earthquake. Okay. The actual geologic event is usually it's the fault slip, which leads to an earthquake or the ground shaking. And in engineering, we call it ground motion parameters. And it consists of different parameters: the peak ground acceleration, the spectral acceleration, spectral velocity. But we will be discussing that later on. But for now, we'll be focusing on the most basic, which is the peak ground acceleration. Basically, it's the strong jerk. When the earthquake starts, it's the strongest instantaneous jerking of the ground. Like, yun yung pinakamalakas na sipa. You're not supposed to speak in Tagalog. Anyway. Also conduct deterministic seismic hazard analysis. This sounds complicated, but this is just basically looking for the worst case scenario. So what we're doing in deterministic seismic hazard analysis is we just try to look at different potential earthquakes. Okay, this could be a historical earthquake, like the previously recorded earthquakes, or this could also be a geological earthquake based on geological studies. One good example is the Valley Fault System. Okay, they put the potential earthquake in the Valley Fault System around 7.2 to 7.6 if I remember correctly. But it's based on geology. Okay? They did some fault slip studies. Okay? And they came up with that number. Okay? So it's not actually it's not a recorded magnitude yung 7.2 to 7.6. No. It's not a historical earthquake. But it is a it is possible based on the geology of the fault. Okay? So once you consider all those scenarios, we just try to calculate the possible effects of the earthquake on our project site. So the project site can be a building, it could be a hospital, it could be a road or a bridge. And then we just look for the worst case scenario, and we usually just adopt that scenario for the engineering design. Alright, let's proceed to the actual exercise. Right, this hazard map part is just basically just about familiarization with hazard maps. So we can just check the seismic hazard maps of PHIVOLCS in this link. Okay. See it? Have you seen this website before?
Yes, sir.
Familiar ka na? Okay. Sa PHIVOLCS. Okay. What subject? Depende. Geology of the Philippines. Okay. Okay, so I mean, it's good that you're already familiar with that. So you can basically just select the region of your site, let's say NCR, and select the city, the seaport area. And then let's say you're interested in ground shaking. Not a parang wala. It's not available. Okay, so sometimes the site better responds if you just input a region. Alright, so let's check this one. Normally, when you have a hazard map, of course, what's important in the hazard map, of course, is the scale. In this example, we have the hazard map of NCR, and this is a intensity map. Okay? So basically, this is the amount of shaking that will be felt by the populace. Okay? And this is partly related to peak ground acceleration. Okay? They're quite related, but they're not. But the difference is that intensity is more of a subjective scale. Remember, a certain scale will cause you to wake up from sleeping, or will cause the objects to fall on your head and kill you, like that. For PGA, or peak ground acceleration, it's more on the numbers which engineers need. Okay? Like PGA point 5 G, or G is the acceleration due to gravity. Okay? So they basically just measure the amount of earthquake acceleration in terms of acceleration due to gravity. Okay? For engineering purposes. Basically, 1 G is approximately 9.81 meters per second squared. Okay? So we have this map, and you have the scale here. It's 1:50,000. Okay. So this is important because, for example, if you're doing a project that's just if you're doing, for example, a road project, okay, or a highway or a freight railroad project that will span like 10 kilometers. Okay? You can imagine 10 kilometers span. And you can imagine 10 kilometers. Right? So, if you're plotting it in a map of 1:50,000, I think it's better to draw it here. So 1:50,000, that's approximately this length. That's 10 kilometers. So one pixel in the map, it is just okay, so you can see here, for example, this is the alignment of your road or your railway project. So one point here is 15 meters. If you're gonna convert it using the scale, 1 point approximately 1 millimeter. That's 1 meter. 15 meters. So the small points, or in this case, you have a project that's big or long enough, such that you just really need the general picture. So, for example, if you're planning the project, you can easily see here that you can you can consider other route options. So, for example, going this way, okay, or you can also go this way. Okay. And it's immediately obvious that this one will be the most driverless. Okay. It has the highest level of hazards first, followed by this one and this one. Okay, so for just generally for big projects or for planning stages of projects, no, hazard maps are useful. Okay, if you're just doing a general planning. But once you start dealing with actual hazards, for example, liquefaction. Okay. Liquefaction usually involves alluvial deposits, particularly the silty or the sandy ones. Okay. And alluvial deposits, I'm pretty sure if you're familiar with the patterns of alluvial deposits, they can change abruptly. Right? So within a few meters, the alluvial deposit might turn into clay or into boulders or cobbles. And that would have a significant bearing on the liquefaction hazard. Okay? So if you're standing on gravels, you don't really have, there's no potential liquefaction or cobbles or clays, okay? As opposed to standing your structure on silt or sand. Okay? And that condition can easily vary within a few meters. Okay? And that won't be easily captured by 1:50,000 map. Okay? Because this is only showing approximately 50 meters per pixel. Okay? So if your project footprint is less than 10 meters square, okay, and you're expecting a variation of conditions in a scale of a few meters, no, you can easily miss out or misinterpret the actual hazard. So it's important to do site investigations. What I also want to show here is the disclaimers accompanied by the maps. You have here usually an explanation here. Okay, so this is a composite map of estimates of maximum intensities that may affect the study area. So this, you can also see here the methods are described here. Okay. And then on the second sentence, you also have a disclaimer here that ground shaking hazard maps do not restrict construction of any structure or land development in areas, as long as it is allowed by the National Building Code or it follows the National Building Code. So in the end, the hazard maps do not really prohibit construction. It's just a guide. Okay, so as long as you're following the standards or the building standards, it's fine. Okay. Okay. So yeah, also has a clause here for emergency response. Okay, and plannings and evacuation. So yeah. So communication is also important in hazard maps. So I think they're trying to avoid here an unnecessary panic among the populace. Alright, that's what I want to okay, so for the exercise, you just have to download two maps, no? Just put in the title, the source, the scale, the size of a 1mm feature, any disclaimers. So this is more of a familiarization exercise. Okay, we're done. Now we have some follow-up questions on the maps. And then I just have here a short sentence. So note that hazard maps provided by various agencies are typically in the scales of 1:10,000 to 1:50,000. On the other hand, most engineering construction plans and blueprints are made at the scales of 1:50 and 1:500. So this is more detailed. This is much more detailed. Okay? And to be honest, this is one of the problems that we encounter in DPWH. Because in our department, we also have our own geologists. We also do our own hazard analysis. And sometimes it clashes with the studies of MGB, because the studies of MGB are done at the scales of 1:50,000, 1:10,000. Okay. So sometimes we have to do a joint inspection. We just have to clarify. We have to do an actual site visit with MGB just to clarify. For example, you have a bridge project in a high flood hazard. So at first it might look like a dangerous idea. So why are you putting a structure in a high flood hazard area? But you also have to consider, of course, the structure. I mean, the vulnerability of the bridge, of course, is meant to traverse waters. So the floods might not matter so much. Also, you have to consider the strategic importance. Okay? We have this concept in earthquake disaster management, the concept of strategic or critical roads that also function as evacuation routes. Okay? So if you don't construct that bridge in that area, you might end up depriving the populace of means to evacuate that area in the event of a large disaster. Okay, so you have a lot of considerations actually. It's not about the size or the magnitude of the hazard. Okay. Okay, so in here we have questions like why do you think we should verify hazard ratings obtained from hazard maps with set conditions? And then second question, what is the point of using hazard maps? Or particularly if you're doing an engineering project, at what stage can it be used? Okay, so it's so you can just answer this with a few sentences or a few bullet points. Alright, then let's proceed with the next part, which is ground motions. Anong nickname mo, Angelo? Sorry. Anong nickname mo? What's your nickname? Jello. Jello, yung mga prof mo ba nagmamask? Yung mga prof mo sa mga lectures, nagmamask pa ba sila? Do they still wear a face mask while lecturing? This is your first face-to-face. Okay, this is also my first face-to-face class. Okay. Ground motions. And so this part contains a few sections. First is the age of active faults. Actually, this is I think this will be discussed in the second lecture next week. But the question here is for a fault to be considered active, what is the maximum age or years of the last rupture of the fault? So basically, we have here an age limit for faults, for me to consider them as active. Okay. An active fault is a fault that is likely to produce earthquakes. In active faults, technically speaking, they're not necessarily incapable of producing earthquakes, but they're just less likely to produce ones. Parang less likely to inactive means less likely to produce earthquakes. But when you're explaining it to lay people, we just simplify it as it's not capable of producing earthquakes. Usually, yeah. So I'm just gonna answer this question. Usually, what?
Sir, sa Abra, sir, yung earthquake doon, sir, active fault ba yun, sir?
Abra River fault ba yun?
Yung last earthquake, sir.
Check natin. Abra. You can check that. Tayong Abra. Abra River fault. Yeah, this is an active fault. Abra River fault.
Pero ano, sir, nalakas yung...
Slip.
Kasi nasa Cavite po kami, sir.
Cavite. Mm-hmm.
Sir, we got the motion, sir.
What part of Cavite?
Imus, sir.
Imus.
Parang may...
Sa may... Imus, Cavite.
Yung pala, sir, sa Abra talaga
Mm.
epicenter, sir.
Were you standing on... Sorry. Nasa building ka ba or nasa ground?
Row house, sir. Subdivision, sir.
Subdivision. Imus is okay, so
Yes, sir.
are you closer to the coast?
Yes, sir. Basta nag-inis.
Yeah, that's well, for one, the earthquake was strong, no? It was magnitude 7. Okay? But still, medyo malayo siya, no? It was like like hundreds of kilometers away from Manila. But if you will, yeah, the ground motion, no? It is caused by various factors, no? Or the actual earthquake that we feel. So of course, one is the size of the earthquake. Second is the distance. So those are the two obvious, most apparent factors. Other factors that are not so much discussed in non-technical settings is the soft, of course, the topography, okay, or the elevation. If you are standing on a mountain or a tall building, of course, the earthquake can get easily, the ground motion can easily be magnified. Okay? So imagine you're here versus you're here. Okay? We call it the flagpole effect, or in technical terms, it's called the topographic amplification. So they just usually multiply the ground motion on level ground by a certain number, okay, to get the amplification that you will get if you're on a mountain or a building. Another is the basin effect, geological basin effect. This is more apparent in large earthquakes. Geological basin effect is, if this is the side view of the geologic basin, and then you have sediments. And this is mostly bedrock, right? Geological basins. So let's say this is volcanics. So this bedrock is inherently stronger or stiffer than your sediments. Okay, this is more stiff. Yeah, if you have a big earthquake, one of the features of large earthquakes is they can generate long period waves. So long period waves, they're like people who can jump. They jump instead of walking. They jump. Okay, they can travel large distances without losing energy. Okay, so when you have a big earthquake, it can generate a long period seismic wave. So this one can easily travel long distances without losing energy. Okay, because they cycle. It will only take a few cycles of vibration to reach a certain distance, because they have a long period. Okay. So once they reach this basin, the waves can easily just once they reach this soft sediment. Okay. So this will disperse, and then once the waves reach the edges of the basin, so this is a stronger rock or a stiffer rock. Usually this will just undergo deflection. So in general, the whole seismic wave will be just trapped inside the basin.
Amplified, sir.
Yeah, it can get amplified. This is one of the factors considered in the Mexico earthquake, I think 1985. Mexico, South America. Michoacan earthquake. In that case, they had an earthquake 400 kilometers away. The earthquake was like 400 kilometers away from the city. But the whole city was devastated. So imagine getting an earthquake from Ilocos Sur, or from Vigan. That can literally hold into Manila. Other factors is the stiffness of your soils, of your shallow soils. Soft soils, usually they can amplify earthquakes. Soft soils can amplify ground motion. Sorry. So if you're in Imos, probably you might be standing on soft sediments or like river alluvial sediments.
Mostly farmlands.
Farmlands ba?
Pero marami namang subdivision.
Okay. Or hopefully it's not due to the construction of your houses. Anyway, yeah, those are some of the factors that affect the ground motion. Okay, the age. So faults that are younger than Pleistocene. Usually Pleistocene is the cut-off age for active faults, or approximately 10,000 years. So it's faults younger than equal to or younger than 10,000 years are considered active. Potential earthquake size from wells in Coppersmith. Okay, so I discussed earlier the basis of our earthquake scenarios. Okay? This could be the scenarios that we usually consider in hazard analysis. This could be based on historical. So the earthquakes recorded usually by instruments or described in recorded history. So that's the historical. The other basis for determining the size of the earthquake is the geological one. Okay, so this is sort of the geological basis for determining the size of an earthquake. And it's based on the study of wells in Coppersmith 1994. Okay. This study is almost 30 years old, but this is still widely used now, even by FIVOX, I believe. Yeah, mostly still applicable, though it has limitations, of course. Kumbaga, it doesn't have a lot of alternative studies for doing this one. Wells and Coppersmith, what they basically did is so I'll just show you the paper. What they did is they just they made a database of all a lot of earthquakes around the world. So they measured the length of the fault rupture, okay? And then the size of the earthquake produced by so the size of the earthquake, the magnitude of the earthquake, and then they also looked at the fault that produced that earthquake. So what was the size of the fault rupture that produced that size of earthquake? What type of faulting happened? Was it strike slip? Was it normal? Was it reverse? Wait a minute. So it started new empirical relationships among magnitude, rupture length, rupture width, rupture area, and surface displacement. Alright, rupture width is. I can remember this one. Rupture area is like the. So if you have a fault, and you're gonna draw it as a plane, as a 2D plane. So let's see, this is the fault plane. And this is the ground that moved to the fault slip. Okay. So this is the length of the fault rupture. So this is the length. Okay. So that's just the this is the distance parallel to the stripe of the fault. And then, I'm not sure about rupture width, but rupture area is the this one. Okay. It's the length times this movement length. Okay. The down dip movement. Okay, so that's the area. And then surface displacement is, I think, is the movement dip direct in the direction of the dip. The fall. So I think this is the displacement. So what Wilson Coppersmith are saying is that obviously the bigger the rupture length, the bigger the earthquake. And the bigger the surface, the rupture area, the bigger the earthquake, the bigger the surface displacement, the bigger the earthquake. And then they also added other descriptors like the type of the faulting, like normal, strike slip, reverse. Stretch. Okay. I'm gonna skip this one and then. Okay, so the database of Wilson Coppersmith is a worldwide database consisting of 421 historical earthquakes. And this one includes shallow focus or earthquakes less than 40 kilometers, continental intraplate, and then intraplate earthquakes of magnitudes greater than 4.5. Okay. So they only focus on the big earthquakes. Earthquakes associated with subduction zones were including plate interface earthquakes and those occurring within oceanic slabs are excluded. So this is one important limitation of this study. It doesn't include subduction zone earthquakes, and uh, earthquakes within oceanic slabs. So I think that includes most of our earthquakes in the Philippines. But still, they don't really have much choice though. I mean, of course, I think VOX is still on the process of upgrading their database, no? So that they can better relate magnitude of earthquake to the size. So I think that's one of the reasons why it's in the protocol of VOX, of course, to investigate earthquakes, that have recently happened, especially the major ones. So earthquakes. But in general, earthquakes are really the whole discipline. It's really still it's really a discipline that's still on progress. There's still a lot of stuff to be discovered on earthquakes. Anyway, so you have here the table of the earthquakes used in the study. Okay, Taiwan, Japan, even Philippines, Iran, and
Most of our references from Japan, right?
most of our
Reference use Japan.
Japan
Unless
similar because of their similar setting.
yes, sir. Some cases.
It depends. Mm, for example, in what references in general?
Since they are always in geohazard, diba, sir?
Mm,
And they are near the Pacific Ocean.
mm.
So, is it reasonable to use some of Japan's geological setting as a reference? Iba kasi yung Philippines.
Good question. I'll check that later. Pero there are a lot of if you're studying the earthquakes, why not Japan? Not really sure if they have. They probably might have literature, no, on relating their fault length for fault area, fault geometry with the size of the earthquake. They might have one. I'll try to explore one of these days. But yeah, that might be reasonable because basically we're part of the part of the Ring of Fire. But I'm not sure if they have the exact same tectonic regime as in the Philippines. Not sure about that. But yeah, for general studies, Weston Coppersmith is just this one is a practical placeholder in place of the lack of studies. I think the one thing that's good with this one is that it has a big database of earthquakes. Though yeah, it doesn't include subduction earthquakes, so that's one big disclaimer. Although I think there are new studies on. There are more specific studies on the type of the fault and the sizes of the earthquakes that it can produce. So what subduction zone or the trenches, what sizes of earthquakes can they produce? So I think there are specific studies for that, and This Wilson Coppersmith is more for the general estimation. Also, I think the paradigm or the current meta for earthquake studies is to do probabilistic studies. So instead of attempting to get a very precise estimate of the potential earthquake size, they just usually use a range of possible earthquake sizes. So you will encounter the Gothenburg-Richter fault size distribution. So what they did is they just did a statistical distribution of earthquake sizes depending on the length, or for example in the subduction zones. I think they placed a hard limit on the sizes of earthquake in subduction zones. I think it's around 8 or 9. Okay. So so if you're interested in doing a really in-depth study, most of the uncertainties in the earthquake correlations are covered in the probabilistic methods. So if you want to do an in-depth study, you can do the probabilistic method, and there is a set of prescribed studies and methods and correlations in sector. It's a study, new NGA. Yeah, this one. They have a big project, an international project that basically seeks to better determine the sizes of earthquakes and their ground motions worldwide. Okay. So this NGA or Next Generation Attenuation ground motion models, they basically have a set of studies prescribed. So we can see here the Abramson, Silva, Bohr, Borzogonia, Chia, and Youngs. So these are different studies that they have different prescriptions for the type of fault. For example, trenches versus shallow crustal earthquakes, and so on. Okay. So, right. So, but yeah, this is a advanced aspect of earthquake engineering. So yeah, let's just go back to the basics. Anyway, we just have to understand this concept first before jumping to those to the NGA project. Right. So going back to the paper, I just wanted to show the formula. Alright. Alright, this is a table of different equations prescribed by Wilson Coppersmith. Alright? So we have different equations here that are using different equations, so depending on what data do you have. For example, this equation, if you only have the surface structure length data, okay, this one is the most commonly available. Basically, the whole face of the fault, or usually what T-Box does is they just they just measure the length of the whole active fault. Okay? For example, uh, they have a fault that's an active fault that's 100 kilometers long. So they just take 100 kilometers, then they apply some factor, because usually active faults do not rupture to their whole length. Usually it's just a portion of the whole active fault. So they just multiply it by a certain factor. I'm not really familiar what number do they use, but usually they just use a portion of the whole active fault length. So for example, if the whole active fault is 100 kilometers, they will usually just use, like, for example, 50 kilometers. Okay. So this is the surface, and so they will just assume maybe that the potential rupture from this fault is just around 50 kilometers or 70 kilometers. But it is really, really rare to use the whole length of the fault. But sometimes, if you really don't have, for like really conservative studies, engineers might use the whole length of the fault just for conservatism. Okay? So it's more of an engineering judgment at that point for like engineers who might not have a lot of data about the active fault in question. So they just assume that the whole length will rupture. Okay. For me, I just use the whole length, no? Unless I have a good, usually for conservatism. Is hidden. Yeah, that's a good question. That's for the blind faults, no? Because when the fault is intersecting a relatively ductile geologic formation, like clay sediments or like soft sedimentary rocks, the rupture might not really propagate. Okay, so if this is the fault, no, the rupture might not really propagate to the surface. Okay, yeah. Unfortunately, there's really no good solution for that. Okay, so you might have to make a judgment. So for example, if you're seeing a fault, and you really have to use your imagination. For example, if the fault is on a critical structure like a nuclear power plant or a hospital, you might have to do some geomorphological interpretation of the area. For example, if there's a fault structure here and there's a ridge that might be a continuation of this fault, you might have to do that judgment. Or as I've said before, in practice, we usually just use the whole length because we're not sure if this is just the actual. We just use the 100% of the active fault length because we're not really sure if this is the whole length of the fault. Okay. So yeah, earthquake engineering is really has a lot of unknowns at the moment. So that's one of the reasons why probabilistic analysis, because probabilistic analysis accounts for all those uncertainties. Okay.
So, geological engineering more on statistical sides?
Eventually everything is going towards that future. But for now, at least in the Philippines, particularly for the engineering projects, usually we just use deterministic analysis. Although for small projects, it's just usually deterministic. For very big projects, like for example, bridges, sea bridges. So, for example, we have I think we have a project that will connect Corregidor to Bataan. No, Bataan to Cavite Bridge. Okay, so it's a big sea bridge. In that project, they're doing both deterministic and probabilistic analysis. We still use deterministic for small projects, and we also use it to check the results of probabilistic analysis. Kasi probabilistic analysis is a very complicated computation. If you just miss out one calculation in probabilistic analysis, you can mess up the whole calculation. So it's also important to have deterministic analysis, so you can have a rough estimate of what the numbers should be. Okay. Going back, you have this equation for surface rupture length. Okay. And then this is the magnitude. And then A and B are like your constants. So in here, they have a value for A and B, okay, depending on the type of the fault. For strike slip, you have this value. For reverse, you have this value. Normal, you have this value. If you don't know the type of the fault, you can just use all. Okay, so you can just use this one. Also, this one has a provision for the standard error of the estimate and the standard deviation. For the exercise, I won't be requiring you to use the errors or standard deviation. Okay? So you just use these numbers. You can ignore the standard errors for now. But for your benefit, if you're using this equation and you want to account for the errors of your estimates, you can basically just use the standard deviation here. Okay, so standard deviation. So if you want to use the standard deviation, you just whatever calculated value you get here, you just plus minus, you just add and subtract 2 times the standard deviation. For example, if you get a magnitude 7 from your calculation here, and you use the all slip type, and you want to account for the errors of the correlation, you just apply plus minus 2 times 2.8, so 7 plus minus 0.56. Okay, and that would be the range of your magnitude. And this estimate will be correct 95% of the time, or 95% confidence. Okay. Yeah, but for the exercise, I won't be requiring you to compute the standard deviation. Okay. Just compute the raw number. Okay. All right. Other equations here are RLD. I think this is rupture length. RLD is subsurface rupture length. All right. So the surface rupture length can be different from the subsurface rupture length. I think that relates to what you asked before about the blind faults. Of course, the subsurface rupture length will always be longer than the surface rupture length. RW is rupture width, down dip rupture width. RA is the rupture area. Okay. Okay. So yeah, I'm just showing where the equation in the exercise came from. Okay. Okay, yeah, basically we have this example. So this is the equation that we'll be using for estimating the earthquake size given the surface rupture length. So we have, I included an example here. Given a potential earthquake involving a fault with a surface rupture length of 10 kilometers, calculate its estimated moment magnitude. Okay. Right. Note that this equation, the Wilson-Coppersmith, will give you a moment magnitude. Will give you a magnitude of the earthquake in units of moment magnitude. Alright, and we have here the solution. So 5.08 plus 1.16 multiplied by the log of the surface rupture length. This will be log 10. Okay, then log 10 is just 1. Okay. And then you finally have this quantity 5.08 plus 1.16, that will be 6.24 moment magnitude. Okay. So that's how you can use the Wilson-Coppersmith equation. Okay, so this is the problem for the exercise. You have a potential earthquake involving a fault with a length of 100 kilometers. Okay. Okay, so for this exercise, just use the whole length, the whole surface rupture length. Okay, just use 100%. Alright, other parts of this exercise include the magnitude conversion. So usually in engineering, what they usually use is either the moment magnitude or the surface magnitude. I think this is discussed on the other lecture, but in general, the internationally acceptable unit of measure is the moment magnitude, because because surface magnitude is usually just about this is more about the strength of the earthquake. Surface magnitude is not really useful when you have an earthquake that affects a very large area, or the fault is affecting a very large area, and the displacement is relatively weak, no? So you can have a big fault with little fault slip, meaning the actual strength of slip is small. It can still release a very big energy because of the size of the fault. Okay. So that's what the moment magnitude is trying to address. It tries to address as well the size overall size, aerial size of the fault. And usually the moment magnitude has a bigger range. I think it can exceed. It can exceed. I think the highest is 9.5, 9.6. Surface magnitude is limited to 8.2. Okay. It cannot detect earthquakes bigger than 8.2. Alright. So these are the two equations that we can use when converting from surface magnitude to moment magnitude. We have two equations because it depends on the size of the earthquake. Okay? For small earthquakes between 6.1 to 3, we can use the first equation. For large ones between 8.2 to 6.2, we can use this one. Alright. For example, we have an example here. Convert the following earthquake magnitudes 5.0 and 8.1. And we have this solution here. Alright. Basically, it's just 0.67 multiplied by the surface magnitude plus 2.07. Okay, it's this equation. Okay. For now, you can ignore the plus minus error intervals. Okay. Alright, so 6.67 times 5 plus 2.07, you will eventually get 5.42 moment magnitude. For the 8.1 example, actually may mali ako sa solution. I used 8.2, this should be 8.1. Let's rectify that. .99 times 8.1 plus 0.08. So this should be 0.9. Okay, proximity is still 8.1. Okay. Okay, for the exercise, you have these five. I just save this new version. Right, so for the problem, you have to convert five magnitudes to moment magnitude. And then the next section is about historical seismicities. Okay, so this is a scenario problem. So you're doing a geological investigation for a building in Manila. I think I need to install Google Earth first. So what we're doing here is we have a an active faults and trenches map of VBOX, and then we also have a database of historical seismicities. Sorry for the segue. So I'll just give you an overview of the exercise first. So you have this data on the active faults maps and trenches. So this is your geological data. And then you also have a database of historical seismicities of historical earthquakes. So this is your historical data. Okay? So, and this historical data is based on the USGS earthquake catalog. Okay? So the United States Geological Survey maintains a database of earthquakes around the world. And then you have this Bautista and Oike. This is a study by VBOX scientists. What they did in Bautista and Oike is they studied his Spanish time records of earthquakes in the Philippines. So I think this was from 1560s to 1889 or 1880s. So at that time we didn't have accelerographs yet. But we do have records of the damage of the earthquakes caused during that period. So in this paper, this is actually a good read if you want to read it for fun. Apparently, the Spanish friars, they were actually good at constructing churches in the Philippines. Churches are actually fortified. So you can imagine the churches have very thick walls. I think in the whole Philippines, all the Spanish era churches are fortified, reinforced. And apparently only like a certain magnitude of earthquakes can only cause damage to those earthquakes. I think it's in the range of 7. Okay? So from there they were able to, and there were also other considerations like occurrence of landslides in different areas. So they just tried to collate all that information, and they were able to generate a relationship between the damage and the magnitude of the earthquake. Okay, and from there they were able to plot historical earthquakes in the Philippines in the Spanish time or the colonial period. Okay, from 1560s to 1880s. Okay. So actually, this is very nice. I mean, I think we're one of the few countries that have this extensive earthquake database. Okay. All right. So what I did personally was I collated all these earthquakes from the 2 catalogs and placed it on a KML file or a Google Earth file. So that's why I'm trying to install Google Earth. So in your exercise, what you have to do is you have to plot the coordinates of your campus, the AUPAM building. You have to plot this in Google Earth and then open the VBOX map. and find the 3 nearest active faults within 200 kilometers distance. So I have this map here showing Mapua Intramuros. So that's the exact location of the Aupang building. And this is what Google Earth will look like once you open the PHIVOX map. Okay, and you can easily see the nearest faults here. Alright, so you have your valley fault system, and then you have some faults from Zambales, from Quezon. Okay, so you can just choose the 3 nearest ones and list them down. And then once you have those 3 faults, calculate their earthquake magnitudes using the Wells-Coppersmith equation. So just assume that the length of the fault is the rupture length of the fault. Okay. So this will not be an exact science because some faults are segmented. Okay. Some faults are not necessarily straight. So just try to
parang i-approximate na lang po.
yeah, just approximate the lengths. And then the third part is to open the historical earthquakes. Okay. And then find the 3 largest historical seismic events within 200 kilometers of their site. List down their date and magnitude and coordinates. So I'm trying, not sure if I can open this in Google Earth Online. But personally, I prefer the desktop version of Google Earth. It's easier to use the desktop version. Alright, so it's working. So this is the fault of PHIVOX overlaying on Google Earth. And then you can also, I'm not sure if you can also open another file. Anyway, I think it's better to just use the desktop version. It's not really easy to manipulate the data here. But yeah, this is just, I'm just showing you the map of PHIVOX. So our project area is around here in Manila. And then immediately adjacent fault is the valley fault system. Okay, so you can see some arrows here labeling the fault. So this is the valley fault system. You have some faults here like the Iba fault and then East Zambales fault. Okay, so some of them are like in broken lines. So what I usually do is I just measure the whole length, the total length. Okay, and I just assume that this is continuous. Iba fault, Gabaldon segment. So you have this one. Sometimes it's difficult to distinguish what the arrows are pointing because you have faults that are basically overlapping. So you have to read them carefully. Okay. Solid lines here are, I think, are the well-studied faults, and then the dashed lines are just inferred faults. Alright? Yeah, but for the exercise, I'd recommend just using the desktop Googler because it's really hard to open this one. Then I'll try to show you the other database. So this is the PHIVOX map. Then sorry, I'm not really familiar with this one. So let's try to open the other database, the historical faults. Alright. Okay, so these are all your earthquakes from like 1600s to 2018. You can click the fault, you can click the earthquake. Okay, and you can immediately see the magnitude of the earthquake. So this one is 6.5. You also have a date of the earthquake. So this one doesn't have an exact date. So it's just 1863. And then the latitude and longitude. And then the source. Okay, this is supposed to be Bautista 2000, but something happened when I was trying to make the file. Okay. So this file is not officially from PHIVOX. So I only made this file. So use caution when using this file. So yeah, you can just click the green dots and you can see their data. Okay. Alright, so that's how you can use the file. So just record the date, magnitude, and coordinates. Okay. In an actual deterministic analysis study, what you will do is you will calculate the peak ground acceleration of all these earthquakes, and then pick the largest one. Okay. But for this exercise, I just removed that part. Okay. Because exercise is already quite long. And then finally, our last section here is the calculation of peak ground acceleration. Okay. So again, peak ground acceleration is like the strongest jerk of the ground during an earthquake. It's the sudden motion of the ground. Okay. It's the peak or kumbaga yung pinakamalakas na sipa ng lindol. That's the peak ground acceleration. Okay. Sorry, makuha. mahirap din kasi mahirap din mag-explain na mabilis mo mako-convey without using Tagalog. Yeah, but I understand you have to speak English, of course, for... Sometimes you have international student classmates, right? Yeah, it's actually disrespectful if you have international students. I studied abroad for a time, and it can be, let's see, annoying or insulting when you're with a group of other people and they're just talking to each other in their own language and you can't really you can't really relate. Anyway, peak ground acceleration. So we have here the old Fukushima and Tanaka equation. If you're gonna speak to other earthquake engineering professors, they will laugh at you for still using Fukushima and Tanaka. Because this is an outdated study. And this is mostly done in Japan. This is mostly the data from Japan. If you want to do something modern, you can use the probabilistic methods as prescribed by the NGA project. But again, in reality, in engineering, civil engineering, most of the methods that we use are really old ones. It's fast, easy to do, and sometimes it's not really the most critical part of the project. But of course, we should modernize, of course.
So, basically, sir, most of the sources are already.
Yeah. For example, in DPWH, we have different standards for bridges versus buildings. Okay? Bridges are modern. The standards for bridges are more modern. What we use in bridges are probabilistic analysis. So
What do you do?
what do I use? It depends on the project. If the project is a bridge, we have what we call the DPWH bridge seismic design specifications 2013. So we have a standard for bridges and it uses probabilistic analysis. So we use probabilistic analysis for that. For buildings, we still use the National Structural Code of the Philippines 2015, and they still use deterministic. Okay, so we just have to conform to that. But if you're like doing project in the private, I also experienced working in the private consultancy. What they do is, I think regardless of the project, they use both probabilistic and deterministic. But of course, ask your engineer on what they prefer. And of course, you have to defend. Of course, if you're proposing something in the private consultancy, if you're gonna give a suggestion, you have to justify it. For example, deterministic. The problem with deterministic is that it gives really big values. Okay? So it can really give you a big value for the earthquake, even if that earthquake is very, very unlikely to happen. Okay? So deterministic, it's commonly used because it's easy to do. the implication of something being easy to do is that one, it's fast to do for the for the engineers and scientists. Second, it's easy to check. Third, is that
Straightforward.
the calculations are straightforward and reliable. I mean, it's robust, meaning you don't have to spend time making sure the calculations are correct. Yeah, but the problem with deterministic is that it gives the values are too big. The advantage in probabilistic is you get the best approximate. I mean, you factor in all the earthquakes in the area. You consider their likelihoods, and you can consider all the scenarios, and you get one number that approximately represents the most likely condition that will be encountered by the project.
More details.
Yeah, it's more detailed. It's more accurate. So yeah, some engineers don't like big numbers because it forces them to design conservatively. And conservative design increases the cost of the project. All right. Yeah, so we have this equation, the Fukushima and Tanaka. So again, I'm just teaching this because this is just the logical step, no? This is the baby step in doing seismic analysis. You can still use this for double checking. If you're doing probabilistic, it's still good to do deterministic just to double check the values that you're gonna get. Yeah, so we have this equation, log base 10 acceleration maximum, or the peak ground acceleration in GALS. And then you have your surface wave magnitude. Okay. So you have this equation. Basically, you need to know the surface wave magnitude of the seismic source. Okay. So the seismic source, yeah, this could be based on geological or historical. And then you also have to know the distance between the project site and the fault. So R is the distance expressed in kilometers. Okay? If the fault is linear, you just have to get the closest distance or the shortest distance. Right, so we have an example here. Example is you have a surface magnitude of 6.2. The distance from the site is 3.1 kilometers. And then the material is soft soil. I have here the equation that is already arranged. Okay, so peak ground acceleration is just equal to 10 raised to the quantity of 0.41 times magnitude minus log 10 of the quantity of R plus 0.032 times 10 raised to 0.41 magnitude minus the quantity of 0.00334 times R plus 1.3. Okay, so you just plug in the values of your earthquake magnitude. So in this case, it's 6.2. and plug in the values of your fault distance in kilometers. Okay? And you will eventually get 10 raised to 2.67742853, and you will get PGA in units of cm second squared. Okay, so this is also in gals or cm second squared. Okay. So this is the uncorrected, or what we call the bedrock PGA. In earthquake engineering, we have a concept of bedrock acceleration. That is the base value. Okay? That's the base value that we will get. No? Most earthquake engineering studies, most of the instrumentation is placed on bedrock. Okay? So most accelerographs are placed on a ideally placed on a bedrock foundation, because it's the easiest to correct, no? Bedrock usually is more or less consistent in terms of behavior. So this value is what we call uncorrected or bedrock condition. And if the site is not on bedrock, you have to do some correction factors. In this case, the site is on a soft soil, so you have to multiply it by a correction factor. Okay? Soft soil, you have a correction factor of 1.39. If you're doing, this is equivalent to the NSCP Class E. But this is just for for illustration purposes. You don't need the NSCP classification. You just need the correction factor. We will discuss this one later in the course, the NSCP classification. So anyway, the correction factor. Here. This should be 1.39, sorry. So for 4 times 139 okay, 661. It should be 661. Okay. Okay, so basically that's the whole exercise. Okay, so for your problem, you have a surface magnitude of 7.2, and then your distance is 6.1, and then your material is bedrock. Okay. Questions? So I'll just upload this corrected version of the exercise file. Exercise 1.
Mas may lang ba kung soft soil magpaano sa tao?
will be dealing with bigger accelerations when your project is on a soft soil. Due to,
Parang mga farmlands din.
it depends, yeah. Normally, if it's farmlands, it depends on the geomorphology, geology, but usually, if it's farmlands or rice lands, the soft soil is usually within 1 to 2 meters. Kasi yun yung cultivated depth, usually less than 2 meters lang yung cultivation. Pero if your farmland is, you have to consider as well the geomorphology. Is your farmland situated on a floodplain? Or is it situated on the foothills? Kasi kung floodplain, malamang malalim pa yung soft soils yan. Probably the whole more than 30 meters pa yung soft soil. Kung foothills, probably it depends. No? Pero in general, you're gonna encounter more soft soils in alluvial or floodplain areas.
Pero sa ganun, sir, parang may soil, geotechnical
Mitigation. Yeah, yeah, you can alter that one. What they do is you can mix some cement, or you can densify. You mix some cement, or you can mix cement. You can also pound the ground with boulders. Cobble-sized rocks to densify them and provide drainage. That's what we call stone columns. We'll discuss that later in the course, I think on the module 2. But yeah, there are mitigation measures for that. But you also have to consider, of course, the structure. I mean, if you're just doing residential structures, it's not really that critical. If it's residential, I think they do something like mat foundations. Kasi in residential, the problem is more on, your problem is not really the acceleration but the differential movement of your house. Kasi if this is your house and due to earthquake, this part moves downward and this part stays, you will get differential settlement. Magkakarak tong gitna or parts of the house. If you do something like what engineers call a mat foundation. So mat foundation is you have like a layer of gravel with geotextiles. So meron ka layer ng gravel and doon nakapatong yung bahay. So in the event of an earthquake or some ground subsidence happens, yung mat mo will move as one. So pwedeng mag-tilt lang siya pero hindi siya mag-undergo ng differential settlement. So pwedeng mag-tilt lang yung bahay mo pero that can be easily fixed. Okay. I-jack mo na lang siya. I-jack mo yung bahay mo. Yeah, so that's for residential. Usually there's a different way of approaching mitigation. Kasi mahal din magpa-ground improvement, yung mga cement, tsaka soil mixing, tsaka mga stone column.
Geological engineering.
Geological engineering,
Ang parang
Yeah, it, it depends. In DPWH, ang problema sa DPWH, marami naman kami pwedeng gawin. Kaso, it's just so dominated by civil engineers. Mahirap kumontra minsan. But if you're gonna work, for example, in the mining industry, and you're a geological engineer, I've seen more colleagues who got really successful doing geological engineering and mining. Kasi civil engineers in the Philippines, hindi sila masyadong well-versed sa rock mechanics. Yung engineering sa mga bato.
Ayun ang edge sa geological engineering.
Yeah, I mean, that's the edge, I think, if we're gonna go in the mining. Also, I think in geothermal industries, yung paradigm nila is papunta na, nagiging more on geotechnical na rin yung ginagawa nila. Kasi, for example, yung mga properties ng mga geothermal reservoirs, important na rin yung geotechnical. So, yeah, I mean, personally, I I'd recommend mining or geothermal.
Geothermal, sir, yung parang sa bataan, sir, yung nuclear?
No, geothermal is hot rocks. Basically, old volcanoes with hot rocks. Yung steam galing sa mainit na bato, it drives the turbines. Yeah, basically it's a steam engine pero your steam is coming from the hot rocks. Oy, questions? Okay. Sure? Okay. Ano pa bang field niya yun? Even petroleum, alam ko nag-incorporate na rin sila ng geotechnical eh. Nagra-rock mechanics na rin sila eh. Pero, not sure about the future of petroleum industry.
Okay, sir, tuturo ka ba ng rock mechanics? Kasi maganda tuturo sa rock mechanics.
Strictly speaking, kaya ko magturo ng rock mechanics. Pero hindi ako binibigyan ng rock mechanics sa subject. Although sa slope stability, anong subject ba yun? Anong tawag dito? Earthworks and slopes, nagtuturo ako ng may konting rock mechanics. Yeah, siguro just be advised of the updated exercise file. Tsaka yeah, thanks for attending. Revise excellent. So, na-meet mo ba yung mga kaklase mo ever in person?
Sir?
Na-meet mo ba yung mga batchmates mo in person or
All batch na po kasi.
ano?
All batch.
Ano all batch?
2014.
All batch ka ba? Okay.
Baka
Batch.
na yung mga kaklase ko na, sir, mga batch 2018 na, sir.
Okay. Ang kasabay mo sila, Maui?
Yes, sir.
Kumusta naman? Nakaka-interact mo ba yung mga younger? Hindi masyado. Anong work ka na ba?
Sir?
Ano? May?
Po?
May ano sabi? May work na sila?
Bago sir. Kasi last year ata nag-graduate na sila sir.
Mga kabatch mo. I mean, yung mga bata. Nakaka-interact mo naman yung mga younger. Hindi masyado.
Hindi na nila sir.
So, ilang units pa yung kulang, detake mo? 50?
Kasi mag-full load sana ako sir. Pero walang nagtuturo yung mga...
Shit. Oo nga, may nag-request kayo ba yung nag-request ng Hydrogeo tsaka Geostat? May nagre-request kasi ng Hydrogeology tsaka Geostat. Kasi nahirapan ako mag-offer ng ibang subject kasi face-to-face na agad. I mean, hindi ko pa na-adapt yung
Di ba ano yun sir, yung rock mechanics sir, tsaka geophysics wala pa ating nagtuturo.
Walang geophysics.
Geophysics.
Wala skianyo. Dati kasi ako yung nagtuturo ng geophysics. Anyway, napunta siya kay Doc Carlo.
Ano dito kasi Doc Carlo?
Ha?
Si Doc Carlo?
And nawala siya, kailan ba siya umalis? Hindi ko alam kung kailan siya umalis ng Makuway. Around 2000, basta early, before ako nagsimula kasi ako sa Mapua magturo 2018. 2018, wala na si Doc Carlo. 2020 yata bumalik siya.
Last year? Ay, 2020.
Basta sometime during the pandemic bumalik siya. Okay. Thanks for participating. Check ko lang kung na-save to.